In this video, we're going to look at dipole-dipole intermolecular forces in a little more detail. These are the attractive forces between molecules that have permanent dipoles. So these are going to be polar molecules. Dipole-dipole interactions are stronger than London dispersion forces, but they are weaker than hydrogen bonding. Let's take a look at an example. Formaldehyde is a polar molecule. This carbon-oxygen double bond has a chi, or electronegativity difference, of 1.4. This is well above the cutoff of 0.4 for bond polarity. That means that the oxygen is going to be hogging the electrons in that carbon-oxygen double bond more towards itself, leaving less electron density around the carbon, leaving it a little positively charged. Above and beyond that, this oxygen has two lone pairs of electrons, which are going to pack a lot of negative charge. Using the delta plus and delta minus notation we learned last semester, we can label the two ends of this molecule. The hydrogen-carbon-hydrogen section gets the delta plus because its electron density has been pulled towards the oxygen. The oxygen gets the delta minus because it's the most electronegative atom in this molecule and because it has the two lone pairs hanging out with a lot of negative charge. We can also draw mu, the overall dipole moment of this molecule, as an arrow pointing from the carbon-hydrogen end towards the lone pairs on that oxygen. This tells us the alignment of the charges inside this molecule. Let's take a look at a map of the electron density. Here we have our formaldehyde, hydrogen, carbon, hydrogen, the oxygen up here. This is the electron cloud that surrounds this molecule full of all of its electrons. It's shaded to show us where the electrons tend to be and where they don't tend to be. Red means more negative, more electrons, and then more green means fewer electrons and therefore more positive charge. You can see that the oxygen up here has a lot of nice red negative charge around it, which represents both its electronegativity and its lone pairs. This alignment means that the red end of the molecule is going to want to interact with the green end of another molecule. The actual dipole-dipole interaction looks very similar to this. We have the negatively charged end of one formaldehyde molecule interacting with and attracted to the positively charged end of another formaldehyde molecule. This stabilizes these charges so that their energy is minimized. And similarly, these formaldehydes could be having more interactions with other formaldehyde molecules off to the right or off to the left. So remember, you want to look for polar bonds and a lack of molecular symmetry, so you know you have a polar molecule. And then stronger dipole-dipole forces will result from larger chi, so that means a bigger charge separation, and also the presence of lone pairs. Lone pairs pack strong negative charge, so they're always going to lead to stronger dipole-dipole forces. If you want to learn about the other types of intermolecular forces, check out the other videos that I've uploaded. See you guys later.